State the difference between a stationary wave and a progressive wave in terms of the energy transfer. So you need to look at the wave's motion. So if you see this diagram here, on top here is a progressive wave. Notice how the wavelength is moving to the right all the time. Then you look at the stationary wave down here. You see how the wavelength is always fixed, not moving? Okay, so this is the first thing about energy transfer. The energy is trapped between these nodes. Whereas for progressive waves, the energy is moving to the right though. Okay, so there are some similarities and differences that you should know. Here's a summary of it that we looked at in the theory video. Okay, talk about the wave profile, talk about the energy, and here, let's go. So we'll say that in a stationary wave, energy is not transferred. You can say that the wave profile doesn't move. That's how you know the energy is not transferred lah. So the wave shape or the wave profile does not move. That's how we see it. Or you say the energy is trapped between the nodes. Oh, let's add an extra note here. Energy is trapped between the nodes. Okay, number 2. We need to talk about the phase of two adjacent vibrating particles. Now, adjacent here means next to each other lah. You sit next to your friend, right? So, next to each other. Let's look at the animation again. So let's look at, let's look at a loop here. I'm going to circle this part here. It is what we call one loop. And let's say I'm going to look at the instant where all these particles are moving up. So I'm just going to draw a few arrows. Okay, and now I'm going to take the neighboring loop, which is this part here. Okay. See the blue color one here? This is loop number 1. All the particles, when they go up together. When they go down together. The neighboring though, when one loop is going up here, this neighboring green loop, all the particles will move down. Now look for that instant in time. Okay, so adjacent particles here, we'll need to choose, let's say a particle on this side and a particle on this side. They will always go up together or down together. It's always together inside a loop. So these are all in phase. All these particles, if I were to draw the dots, they all either move up together or down together. Now, if you look at the other comparison, let's say up here, okay, if I were to look at any two particles, like maybe these two that I draw lines, sometimes they slide up together, sometimes they slide down together on the wire here, 2 wires. So it really depends. There's no fixed pattern one. It can be in phase, out of phase. So here when we want to talk about the phase, we can say, you want to talk about stationary wave? Okay, let's talk about stationary wave. So in a stationary wave, here, adjacent particles are in phase. Most of the times they're inside the same loop, we call that. Okay, so if I were to draw like this, the wave is actually dancing up and down. So it means if you have two friends here, they're gonna both go up together. You want to talk about progressive wave? Sure, you can say the vice versa. In progressive wave, you only get 1 mark. Particles are out of phase. Are out of phase. Not in phase basically. They can move anyhow. One can move up, one can move down, both can move up, both can move down. I don't know, man. So many. Okay, let's look at our scenario here. So we got an open tube. Longitudinal frequency. Okay. So the speed of sound in the tube is 340 milliseconds. The length of the tube is 0.6. Stationary phase form with a antinode. What's antinode again? Antinode is where there's maximum displacement. Lots and lots of movement. Okay, this occurs at the end of the tube. So if you want to draw, it should look something like this lah. Okay, antinode means lots of displacement. Okay, lots of displacement. Lots of displacement. Lots of displacement. Okay, and this wave here is going to be dancing up and down like this. So to show this motion, we add a dotted line to say like, oh, maybe a short time later it would be in this dotted line position. So that's how it would look like. It's a good practice to learn to draw stationary wave. Okay, so what is antinode? We will describe, right? So we just say max displacement. So let's put in the proper word here. Maybe we won't say displacement. Let's use a better term. Amplitude. Because a particle, let's say this dotted particle right there, always will have that amplitude at that position. Whereas a node here, always have no amplitude. So let's use the word amplitude instead of displacement. So here is where there is a position where amplitude is maximum. So use a better word. Let's use amplitude instead. Okay. So this is a B1 mark. Let's see. What next? What's the distance between the node and the adjacent antinode? So let's see. Antinode is where? We just said those are the dots with no amplitude. These are the nodes. Node. So we want to find the distance between node and antinode. Okay. Let me tell you first. If you see this pattern, this is what a loop between two antinodes. Okay. This loop is half a wavelength because one wavelength is like this. Okay, this is wavelength. So loop is only half lah. Remember, we have this part also. Okay, so here, this distance is lambda over 2. Or you can say from, let's say antinode. Sorry, node to node. Or antinode to antinode. Also lambda over 2. So here when they ask node and antinode, let's see on the right here, got some space. If this is lambda over 2, node to antinode here is lambda over 4. So we say, lambda over 4. Okay. How do we chop this up? Do we need to chop this up? Yeah, I think we don't need to use lambda over 4. Let's just chop it up. Just some straight math. Okay, from all the nodes, let's chop 1, 2, 3, 4, 5, 6 sections between a node and an antinode. So we just take the whole length of the tube, which is 0.6, divide by, what's the number again? 1, 2, 3, 4, 5, 6. Okay, 6 sections. So 0.1 meters. Good to keep at least 2 SF, So let's put 0.1. Put the 2 SF inside. 0. Just in case. Okay, next. So now we need to find for the sound amplitude the wavelength. Okay, just now we got that lambda q there. How do we find that? Let's go back to the diagram. For wavelength, okay, we just now said that this short thing would be lambda over 4. Okay, so really you can take whatever distance you want, whether it's a 0.1, because we know this is 0.1, is lambda over 4. Also you can do that. So let's put that down here. So one option is the 0.1 is lambda over 4. So you can say lambda is then 0.40. Put the 0 in. 2 SF at least. Okay, this is one alternative lah. Or you can say, miss, this entire tube is how many half wavelengths? Let's do it. 1. Ooh, wrong color. Whoops. Sorry, lambda over 2. And another lambda over 2. Can we do that? Okay. 3 lambda over 2s is the whole length, 0.6. So, yeah, we can do that too. So we say 3 lambda over 2s is 0.6. That works too. Up to you. So I'm going to write the alternative here. 3 lambda over 2s is 0.6. La 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 la. Okay, let's find the frequency now. So frequency, we need to know V equals to F lambda. Okay, just now they did tell us there was a V somewhere. Where's the V? Speed is 340. This is V. Okay, So let's put the 340, the frequency and the wavelength that we just got, 0.4. Okay, so you should get a frequency of about 850 Hertz. If you can run it off to 2SF, that's good. Okay, so here usually you get 1 mark for your speed equation. So please remember this equation. This is for bonus marks. Then if you get correct calculation to the end, that's your accuracy point. Okay, right, last part. So determine the frequency, minimum frequency of the sound from the loudspeaker that produces a stationary wave in the tube. So you want here a minimum frequency. How does that look like? Okay, well, you see this one. The way to make the frequency smaller, how would you change this antinode and node setup? If you want minimum frequency, so you need the frequency to decrease, means you need the wavelength to become longer. So let's draw some diagrams here. Okay, so just now you have a high frequency. Your wave looks something like this. Okay, let's not draw so many like this. Let's use dotted lines so we are less confused with the drawings. Okay, so like this. Okay, so the example of a higher frequency. So you want a lower frequency. Maybe you won't have so many loops inside there lah. So maybe something like this. Lower frequency. So there's less what we call loops. And the wavelength is longer because the wavelength is originally here. Hey, where's my wavelength? My lambda over 2 is here. Just now my lambda over 2 is very small. Lambda over 2. So you want the minimum absolute lowest is, you need to know that for an open tube means one end is open, the other end is open, means both ends must be an antinode and an antinode, which means it's just like this and like this. That's how a sound wave that graph would look like if you were to draw that. Okay, so that's a really long wavelength. Okay, what was the length of the tube? 0.6. Okay, so let's see, 0.6 is this whole length, meters. And where's my lambda over 2 again? Lambda over 2 is now the entire pipe. From antinode to antinode or node to node. Okay, so remember, lambda over 2 distance is antinode to antinode or node to node. Remember this. Okay, let's do the maths. So lambda over 2 here is our 0.6. Means this wavelength, as the minimum, is 1.2 meters. Okay, let's... How do you find... Wait. You need frequency. You need to recalculate again. Can. Okay. So one method is you recalculate the whole thing. So we do the second step. Okay. Second step is V equals to F lambda. What's the frequency again? Okay, sorry, forgot. 340 frequency and 1.2. Giving about 283 or 280 Hertz. Okay, so this is one method you recalculate everything. So I'm going to show this here. Is there a shortcut? I like shortcuts. But the shortcut that you want to use here, you need to know how the waves will change. So let's go back all the way up here and see. Just now with this frequency, we get this whole stationary wave set up with 4 antinodes. And that was a wavelength of 0.4. Okay, so let's write that down. The first original lambda was 0.4. Then we calculate a new lambda minimum was 1.2. So if you look at the ratio of these two, this is about times 3. So you can say, so your frequency will be divided by 3. So the frequency of the minimum will be whatever original frequency divided by 3. Okay, so let's list it out. So original frequency was 850. So now my minimum frequency divided by 3, 280. Here, divide by 3. So ratio does help if you have many stationary waves to deal with. Okay, but I think that's all for this question. See you in the next one.